All right, good morning, everyone. Happy Friday. Let's take a look at your work here. So if your books aren't open, can you do so now? We're looking at page 342 and a variety of questions. I think maybe the list I have up there is slightly different than the list that I gave you. Maybe 10 is not there. Is that right? Yeah. Well, I mean, you could do it. I don't know why the lists are different. What we learned yesterday is that the equation of the function y equals c to the x produces a graph that has one of two different general appearances to begin with. One is it could be an increasing function like graph B that you're looking at here. Or the second option is it could be a decreasing function like you're looking at in graph A on the screen. And the idea is that when c, the base, is greater than 1, it's an increasing function, increasing exponential function. But if c is between 0 and 1, it's a decreasing exponential function. Any function of the form y equals c to the x has to have a c value that falls into one of those two categories. You cannot have 0 as a base, you cannot have 1 as a base, and the base must be positive, so you cannot have a negative number as the base. Any of these graphs that fall into this category, and all of the equations in number 3 do, will all have a horizontal asymptote on the x-axis. We'll have a horizontal asymptote on the x-axis, and they will all have a y-intercept of 1. I will warn you that the graphs that your textbook generates are not, they're pretty poor graphs. Because, for example, if you take a look at this graphic here, it just seems to be a flat line, and it shouldn't be. It has to be continually getting close to that asymptote on the x-axis, which is why when I tell you to graph these, I say, you know what you should do is graph it only to about here and then just put an arrow on it. And if you draw in the asymptote, then it becomes obvious what that arrow means. It's getting closer to that asymptote. The other thing we learned is that doesn't really matter. I don't think there are any here. Well, number 12 is, when you start to look at something like number 12, where you have exponential growth, and the growth is 1.27% per year, one of the things we learned is that that means that at the end of every year of growth, the new population will be 101.27% of what it was, which means your base is 1.0127. And that means we're going to have a graph that mathematically will look like this, with that growth rate and this asymptote. But the x-axis here is time, and this is time equals 0, so you can't have a negative time, which means that this graph starts at t equals 0. The domain is not any real number. The domain is t is greater than or equal to 0. And by the way, when you read this question, 0 is the year 2011. Okay? The other issue, though, is if you just said this is y equals, I'm going back to this idea here, y equals the base to the x, which we modify here and say y equals the base to the t, this is not correct. This is not the correct function, because this would have a y-intercept of 1, and the y-intercept here is 7 billion. So how do we create a function that will still have that growth rate of 101.27%, but the y-intercept will be 7,000? The answer is we kick this to the curb and we say it's y equals 7 billion times 1.0127 to the t. And I don't know why I didn't just write 7 and say the y-axis is in billions. So that was the other thing we learned, and we're going to extend that today. But the other thing we learned is when you do that, you get this function. And all of a sudden, it's kind of a shifty move. I've changed the c to a b. Because on your formula sheet, we're going to see a formula today where it's b, not c. But that's okay, because really, this bit of business here, I could have used b instead. It's just a letter, right? So all that being said, does anybody have any questions from any of the assigned problems? Go ahead, Janessa. Okay, let's look at number 10. So the CANDO reactor, I think it's been decommissioned, was a reactor that used uranium-235 fuel. It's a nuclear power plant, basically. Used uranium-235 as fuel. The half-life is approximately 700 million years. What exponential function can be used to represent? Okay, so here we go. Did I assign 10 in your handout? No. I'm going to say I'm not going to explain it right now, but at the end of this lesson, we're going to do this question. Okay? And that's why it's not assigned. Is there something else you need to learn here? Just so everybody knows, it's not possible to write the equation for this function of the mass of uranium-235 remaining using this formula. This formula needs a modification to it. It is, for you physics 30 people, possible as long as you use t as not actual time, but t as number of half-lives. Then it would work. But you know, the physics 30 people are in a minority here, and this is not a physics 30 class. So, by the way, when you see how it's done in math class, you might prefer the math method, because the math equation we're going to use is good for radioactive decay, it's good for compound interest, it's good for any type of exponential growth or decay. And if you're in calculus, there's an even better one that works all the time for anything. Anyway, I'm going to come back to this one, and that's why it wasn't assigned. Okay? Any other questions? All right, let's move forward. So we're looking on page 5 of your unit handout here this morning. We're going to be looking, first of all, at transformations of exponential functions. And I really sometimes feel as though when I take a look at these first two bullets or goals, apply transformations to y equals c to the x, and describe transformations of exponential functions, I always feel as though I shouldn't need to have a special lesson on this, because you know what transformations occur based on the parameters a, b, h, and k. We have an issue here, though, and it's why your textbook uses c and not b, because the parameters for transformations are a, b, h, and k. And if we use b for the base and b for a horizontal stretch / reflection, we've got a bit of a conflict. Okay. That being said, we are going to be using b when it comes to this third bullet, solving problems involving exponential growth and decay. First example, or the warm-up rather, it says if f of x equals c to the x is changed to a f of b bracket x minus h close bracket plus k, what's the equation of the new function? We've done this so many times, but I don't want to minimize the importance of it. This, including the f, but not including the a, this is f of a thing. So just looking at this function, it's f of x equals c to the x. If I said, what is f of 5, it would be c to the 5. Yes? If I said, what is f of kitten, it's c raised to the kitten. And, I'm not trying to minimize the importance of symbols in math, but these symbols are just squiggles on paper, ultimately. They mean things, but they're just, the number 5 is just represented by a certain pattern on paper. So all we're talking about here symbolically is a substitution in for x of whatever f is of. So the highlighted part in yellow is f of b times x minus h, which means that that part becomes c raised to the b times x minus h. So our new function is y is equal to a multiplied by f of b times x minus h plus k. And this is no different than if, well, I'll give you a second to write it down, and then I'll just say a couple more quick things about it. This is no different in principle than the following. That if I said f of x is x squared, and I want to determine what y equals a f of b bracket x minus h plus k is, it will be y equals a times, well, f of b times x minus h would be b times x minus h squared plus k. This middle part is always just f of b times x minus h. It's what you get when you put in for x b times x minus h. If this was sine of x, then it wouldn't be squared, it would be sine of b times x minus h. So that's it. And I guess what we're saying is you should recognize that function, this whole thing, as simply being y equals c to the x that has undergone a bunch of transformations. Vertical stretches and or reflections, horizontal stretch and or reflection, horizontal and vertical translations. And we're going to put that into action here to begin with the example. Describe the transformations that are needed to make f of x into g of x. So when we look at g of x, there are parameters that g of x has in comparison to where it came from, which is f of x. And I want everybody to write down a, b, h, and k, and I would like everybody to take a minute here and determine the values of each of those 4 parameters. And again, I hope it makes sense to you what I said earlier. I feel as though we shouldn't have to do examples like this because you should already know how to do it. The function is 3 to the x, so the function is being multiplied by 2, which means a is 2. X, well, it's x minus 4. X changes to x minus 4, so that means that h is 4 because in our general form of transformations for an equation, it's x minus h. I see that I've got this plus 15 as an afterthought, which means that 15 is k. And there's no coefficient in front of the independent variable other than 1. There's no 3x. And by the way, if it were that, h would not be 4 because you would have to factor that 3 out. It's not this, but I just wanted to make that point. So b is 1. So what are the transformations? We have a vertical stretch, bless you, by a factor of 2. Again, you should know by now, but you don't write that on a diploma exam or on my exam. For a written response, you say there is a vertical stretch by a factor, and you write those words out of 2. You can write the number 2. You don't have to write the word 2. We have a horizontal translation of 4 units to the right and a vertical translation of 15 units up. And that's it. There's nothing else that's happening here. Any questions with A? All right. The next goal is, and I don't think you would ever be expected to do this specific graph on a diploma exam. This is more for us to learn. What we want to do is now graph both of these functions. And this is actually a good opportunity for us to review what f of x equals 3 to the x looks like. I'm going to use the red dots for the original function, and I'm going to use the brown dots for the new function. If you like, for the original function, you can put a dot, and for the new function, you can put a dot with a circle around it, or a square around it, or a triangle around it. I don't care. It's a good opportunity to review what y equals 3 to the x looks like. Both of these functions, by the way, regardless of which one we're talking about, will have asymptotes, horizontal asymptotes on the x-axis, right? It doesn't matter. Because, well, actually, you know what? I totally misspoke there. Let me back up. And I'll ask the question. 3 to the x will have a horizontal asymptote on the x-axis because y equals 3 to the x matches y equals c to the x, and we know that's the case. Can somebody tell me why this new function will not have a horizontal asymptote on the x-axis? Well, right, the whole graph at some point is shifted up 15, so that's going to move that asymptote to 15. Okay, we'll come back to that though. Let's graph y equals 3 to the x based on what we learned yesterday. Pretty simple. Y equals 3 to the x has an y-intercept of 1. I'm a little hesitant in actually drawing the curve that we're going to get. I think I'm just going to leave it as points because it's going to be pretty difficult to draw that in there. And we know that every time, I might draw the curve. Every time we go over 1, y is tripled. So when I triple 1, I get 3. When I move over another 1, I triple it again, and I get 9. When I triple 9, I get 27. That's 25. 27 would be about here. When I triple 27, I get 81, and 81 is off the grid. So this is what f of x equals 3 to the x looks like. And you know what? Let's not worry about drawing it in just yet. We might draw it in later, but that's unimportant. You know that if you were expected to graph this, you would draw the curve in. That's not the purpose of this exercise, though. So how are we going to graph the new function? Well, we're going to do transformations. I'm going to start with this point right here on the original function. And you're not going to draw it in just yet. We're going to think about what happens. The first thing that happens is it gets doubled vertically. So it is going to be at 2. Then it shifted 4 units to the right and 15 up. But just a second here. Will shifting any of these points, no, let me back up. Will stretching any of these points vertically by a factor of 2 change the location of the asymptote? No. Will shifting any of these points to the right 4 units change the location of the asymptote? No. The only thing that's going to change the location of the asymptote is that k value, so we can right out of the gate draw in that asymptote. And I'm not using different colors for the asymptotes. We can draw that new asymptote at 15. So Let's go back to this brown point. This brown point is now 2 above that asymptote. I need to shift it 4 to the right, 1, 2, 3, 4, and then 15 up. But think about this. If it is currently 2 above the old asymptote, and the old asymptote was moved up 15, and I move this point up 15, it is now going to be 2 above the new asymptote. In other words, I can start plotting these points based on their relative position to the new asymptote rather than counting vertical shifts. For example, if I were to take this point, which is 3 above the asymptote, and I stretch it by a factor of 2, it's 6 above the asymptote. I just have to shift it over 4 and replot it in that position so that it's 6 above the asymptote, the new one. So I go over 4 and up 6. And if you're really on top of your game, you could actually plot this point right here, not only in relation to the new asymptote, but in relation to this point. Right? For example, this point is 2 away from that y-intercept, 2 away from that first red point. I'm going to double this first of all. So this is 9. I double it and I get 18. It's 18 away from the old asymptote. I move it over 4, and I just make sure that it's 18 above this one. 5, 10, 15, 18. And I think you get the idea here. I said we wouldn't worry too much about drawing these. I guess I'll give it a crack. I always feel as though sometimes when I draw these, I end up destroying what looks like a beautiful picture. But I'm going to give it a crack. Here we go. That's not bad. That's pretty good. A little shaky in the middle there. Too much or not enough coffee this morning. I can't tell which. And then this one would be, I'm a little off kilter there in the middle, but you get the idea. So in terms of g of x, what's the equation of the horizontal asymptote? What's the y-intercept? What's the x-intercept? What's the domain and range? Well, the horizontal asymptote is at y equals 15. I really hope it's not some big shock to you that it's always going to be y equals k. When we transform y equals c to the x, it's always going to be y equals k for that asymptote. The y-intercept here, well, let's walk away from the y-intercept for a second, because there's no way, listen carefully, there's no way for you to determine the y-intercept by using transformations. Because this old y-intercept doesn't transform to the new y-intercept. That's not how it works. We'll come back to that. X-intercept, you can see there are none. Domain and range, well, x is any real number. You can tell that. And the range, y is greater than or equal, nope, y is greater than 15. I said initially y is greater than or equal to, why would that be incorrect? Riley, do you know why I can't say y is greater than or equal to 15?
Because it would never hit that.
Right, it never reaches that asymptote, so it's not equal to. This is y is greater than k. The asymptote is always y equals k. Is the range always y is greater than k? Why would it not be?
If you have a graph on the opposite end of the asymptote?
Right. So that would mean, in other words, if this 2 were negative, if a were negative, then it would be going down and y would be less than that number. Let's find the y-intercept, though. The y-intercept is found by letting x equal 0, which means we're just going to take this function and figure out what this is. And I don't want to waste time today simplifying fractions. Let's just use our calculator and convert the result to a fraction. And then you can double check to see if it matches what I get. I could be way off kilter here, but I want to say 1217 over 81. Is that right? Don't ask what went on in my head to get that, okay? I'm a product of a non-calculator math education. So the y-intercept is 1217 over 81. Can you figure out what that is in decimal? I mean, you probably already have it in decimal. What is it?
15.02.
So it's pretty darn close to that asymptote, isn't it? 15.0 something. All right. Let's take a look at the next one. The idea here behind the first example, everybody, is for you to develop some rules so you don't need to look at the graph to answer these questions. For example, well, we'll get to that in a bit, but what are the transformations here? We have a vertical reflection because A is negative 1/2. We have a vertical stretch by a factor of 1/2. We have a horizontal stretch by a factor of 5, the reciprocal of B, and we shift this 5 units down. I hope we would all agree with that. That being said, you know me, I make silly mistakes. Are we in agreement on this? Does everything that I've written make sense based on the fact that A is negative 1/2, B is 1/5, and K is negative 5? H, by the way, is 0. The horizontal stretch is always the reciprocal of B. We're on the same page here? Okay. The idea behind doing that first example, and it's why I said let's not worry too much about graphs, is that you want to learn from it to answer the questions in terms of properties of this graph without necessarily graphing it in detail. For example, I know that if the vertical translation is negative 5. You don't need to draw this. I'm just drawing it as an instructive tool, that the asymptote will be down at negative 5. Yeah, I think you don't even need to draw this. You can just picture it in your head. So the equation of the horizontal asymptote is y equals negative 5. Let's jump to the domain and range. The domain is any real number. You can take 3 to the x, which looks like this, and do anything in the world you want to it in terms of a, b, h, and k. It's not going to change the domain. This thing extends from negative infinity to infinity. You can't change that. If you shift it to the right, even if you shift it to the right 10 gajillion, it's still going to go to infinity in the other direction. The range is related to this k. This is at y equals k. What will the range of this be? Joel?
Y is less than negative?
Right, that's just what we were talking about in the previous example. Because this has undergone a vertical reflection before it's been shifted down, that vertical reflection folds the graph below the asymptote, so that 3 to the x would look like this, negative 3 to the x would look like that. Then it's also stretched and shifted. But the bottom line here is you're going to have y is less than k, which is negative 5. Based on that, it's going to look something like that. Not precisely, but this is the point I want to make. You don't have to have a perfect picture. I can see looking at that that there's no x-intercept. And I'm kind of avoiding problems right now where we would have to find an x-intercept by making y 0. Because if you make y 0 with an exponential function, you have to solve for the exponent. And you just don't know how yet. You don't know how to rearrange an equation for an exponent. What's the y-intercept? Well, the y-intercept will be h of 0. So you're going to run all this through your calculator and get negative 5.5. This is not a difficult thing. I don't have to use some kind of weird wizardry here to figure out it's negative 5.5. 3 to the 0 is 1. 1/5 times 0 is 0. 3 to the 0 is 1. So you have negative 1/2 minus 5, which is negative 5.5. Any questions with that example? All right, this is not a long lesson. We have one more thing we have to learn here in one example. And because it's not a really long lesson, I'm going to hand back your last unit exam again today so you can spend more time in detail going over it as well as doing some problems related to this. All right, so this whole thing I want to spend a few minutes talking about is going to be something that not only do we use today, we're going to use tomorrow, we're going to use the day after, you're going to use all of the time. Anytime you have an exponential growth or an exponential decay. And this formula that we're going to be talking about is valid as long as there are no horizontal and vertical or vertical translations. And I'll be honest with you, I cannot think of any application of exponential growth or decay where there would be a transformation by shifting up, down, left, right. It just doesn't happen. We're talking here about radioactive decay, compound interest, population of mice in a barn on a farm, population of virus in the world, value of a rare magazine, value of a car that's getting older, anything that involves exponential growth or decay. And this is a little bit different than what we did yesterday. The difference is yesterday we did this. But yesterday, every example we did where we used that formula I just wrote down had t measured in, say, years. And what was happening every year. So the population was changing by 5% every year. The radioactive decay was changing by a half every 1 half-life. So this exponent was always how many applications of change there were, how many times it was divided by 2, how many times it was raised by 5%. Well, now we've introduced another parameter. And listen, there's certainly a way to explain how this parameter of p is related to a horizontal stretch. I don't want you thinking that way, though. Okay? If you want to challenge yourself to try to make a connection between this formula and what we just talked about, which is transformations, feel free. It's not important. This is on your formula sheet. What do you need to know? The first thing you need to know, and I make a big deal of this because I think it's crucial, is that these two things are variables. Those two letters are fundamentally different in this equation than any of the other letters. What we're talking about here is if you translate that equation to a graph, we're talking about y here and t there. They're variables. What are the other things then? What do we call those other things? Brody, do you know?
Parameters?
That's right, they're parameters. And there's, you know, some people might not think it's a big deal. I think in learning math, I think it's very important for you to understand that these are variables But the other things are parameters. So A is a parameter, B is a parameter, P is a parameter. And the reason why I think that's important is a parameter is a constant for every situation. So for the radioactive decay of uranium-235, A, B, and P will be numbers in the equation, but Y and T are variables. T is the length of time, and Y is the amount of stuff left. So if you talk about the variables first, and I know I can easily over-highlight stuff here, but the variables are clearly what's on the graph. T is the time that's gone by. Y is the amount of stuff you have. The number of mice that are in the barn. The value of the rare magazine. The value of my truck that's depreciating. It's something, it's some quantity that's changing. A is the initial amount. That didn't change from yesterday. We learned that yesterday. A is the initial amount. B is the factor by which things change regularly. So B is the factor by which things change. There's a lot of information here, but for example, if you're talking about half-life, don't worry about the 34, half-life means things are being multiplied by a half regularly. So B would be a half. If a population is growing by 4%, then it goes from 100 to 104%. B is 1.04 because it's the factor that the population is changing by. Factor means multiply. If the value of something decreases by 12% regularly, then B is 0.88. And I want everybody to just see if you can figure out where I'm getting the 0.88 from. I'm losing 12%. So if I take whatever I have, that's 100%. If I subtract 12%, that's 88%. That's where I'm getting the 0.88 from. If I tell you that interest is being calculated, I don't want to do that one yet. Okay, ignore that last one. Okay, don't worry about the last one. Okay, so that's what I mean when I say in your notes that B is the factor by which things change. P is the length of time it takes for that change to happen. We need to know this. So if I go back to my first example here, if the half-life is 34 years, well, B is a half, B is 0.5, and it's happening every 34 years, so P is 34. If the population is growing by 4% every year, well, then P is a year. If the value is declining by 12% every 6 months, then P is 0.5 years, or 6 months, depending on what unit of time you want to work with. And what's going to happen in the coming days, our final example is going to take us very little time. What's going to happen in the coming days is we will use this more and more and more and get more and more used to it. But this formula is on your formula sheet. So, number 3. Radioactive element, I think it's pronounced americium, is used in household smoke detectors. How it works, if you're curious, this radioactive isotope emits particles, and as long as those particles are being emitted and they have they have clean air to go through, they hit a detector and nothing happens. But as smoke particles get in there, they stop those particles that are being emitted from hitting the sensor, and then the alarm goes off. Okay. The half-life is approximately 432 years. The average smoke detector contains 200 micrograms of americium. What's the equation relating the amount of the americium remaining to the time? So, when you look at this equation, what is A? A is the initial amount. 200, sorry, physics crept into my brain there. 200 micrograms. What is B? Jesus doesn't tell us what B is. It doesn't tell us how it's changing. It doesn't say it's increasing by 2% or decreasing by anything. What is B? Yeah. 0.5. This is just what we need to know. Unfortunately, let me write this down first. 0.5 is exactly 1/2, so there's nothing wrong with writing it. Unfortunately, there was a time on diploma exams in the 30-level courses in math that they always said, by the way, the half-life is the time it takes for half of it to go away, or half of it to remain, which are the same things. But then over the years, they stopped putting that for some reason. Sometimes they do, sometimes they don't. So we need to know that half-life means B is 0.5. And P is how many years it takes for it to happen, which is 432. And we're done. We just have to load those three parameters into the equation and have y equals A, which is 200, times B, which is 0.5, raised to the t over 432. Two things to round this out. For you Physics 30 people, in Physics 30, your formula is, it's that stupid formula that has n's everywhere. Should ring a bell. The exponent here is the number of half-lives. But in Physics 30, we learn if you take the total time and divide by the half-life, you get the number of half-lives. So it's the same formula. The other thing I want to point out is, I could ask you more stuff here, but I've designed this unit so that we get more time to review the previous unit. I could ask you things like, how much of the americium is remaining after 500 years? Because, and listen very carefully, I could just ask you that from the beginning. I could not even say, find the equation. I could say, how much is left after 500 years, which would mean you would have to make this equation and put 500 in for t. Or I could say, you know, the smoke detector is no longer any good if that level drops to 190 micrograms. How many years is the smoke detector good for? In which case you would do this and solve that equation. But you don't know how to solve that equation algebraically, so you would solve it graphically. I don't make any claim that these numbers are accurate. I don't know how many years you're going to get here, or if it's still going to be good when it's at 190. I'll work it out once we get started on today's practice stuff. And then we can have a physics conversation if you like. A whole slew of different questions to practice. Whenever it says graph, don't. You can if you want to, but I'm saying you don't have to. Okay? And I'm going to hand back your Unit 4 exams again so you can take a further peek at them. Give me a minute to do a couple of quick things at my computer and I'll be right with you.